In this video, we're going to talk about several methods to solve first order differential equations. Solving first order differential equations. Solving first order differential equations. So what is a first order equation? So you can write a first order equation as dy over dx equal a function of x and y, or you can write the same thing as y prime fxy. If there is no confusion, we write it like that. So we assume that x is the independent variable, and then we assume that y is the dependent variable. Okay, so let's go by case by case. So the first one is what we call the basic integration. Basic integration. So under basic integration there are two types. The first one is what happened, the derivative simply becomes a function of the independent variable only. If the function is a independent variable only, what we're going to do, we're going to integrate with respect to x. So we're going to integrate with respect to x. So if you do that, because that's the derivative, so you get the function y back, and then here just the integral of the function. So that's the easy one. The second case. So in the second case, what will happen, y prime becomes a function of the dependent variable. So if this case, you cannot just integrate like that, because the function on the right side is a function of y, not a x. So the integral is meaningless. So what we're gonna do first is we're gonna write this upside down, because you can write this one as dx over dy equal 1 over gy. But make sure that before we do that, we want to make sure that you can do it, because when you try to upside down, you might have division by zero situation. So you need to consider them separately. Okay, so now you can see that this is the first type. So what we're going to do is we're going to integrate this one with respect to y. So integrate this one with respect to y. So you're going to get x as the integral of 1 over gy dy. So now after we get that, we can solve for y. After we finish this, then what we can do is solve for y. Plus you also need to add the degenerate cases, plus other cases. So plus other cases. So what are the other cases? You're going to get cases like y equal a constant. That's kind of situations. So so that's you need to consider separately, because you divide by you make it upside down. So that's the first type. And then as practice problems, you can try these. So exercise 1a. So you can say y prime equal x squared minus cosine 2x plus e to the negative x plus 3. And as another example, you can say y prime equal y over y squared minus 3. So you can try those two, and you can see the answer in the description. That's the first type. Let's go to the second type. So what's the second type is what we call the separable method. Separable method. So what's the separable method? Sometimes what happens when you look at the differential equation, the function fxy you can write as a product of x and y. So sometimes this is the case. You can separate them into x and y if this is as a product, not a sum. It should be as a product. So a product. So if you can do that, what we can do, we can separate the two variables. So what we're gonna do, we're gonna bring we can write this as dy by dx. So we can write this one as dy. We're gonna bring the y term to this side, and then we're gonna leave the x terms on the other side. So that's the x term. So this is the x term, and then we can integrate that. So that is the separable formula, and then you're gonna integrate the two sides, and then at the end you're gonna solve for y. So you do that, solve for y. So as exercise problems you can try these. So these are problems that you can try. The first one is y prime equal x squared y plus x squared, and part B you can try sin x y prime equal e to the y tan x. You can try those two for separable methods. So let's go to third method. So what's the third method? So number 3, what we call the first order linear equations. First order linear equation. So when you have first order linear equations, we can use the integration by parts technique. Integrating factors method. Integrating factors. So we can use integrating factors for that, for the third case. So we need to write the equation in a special form. We write the equation in the standard form, that what we normally call y prime plus px y equal qx form. So we can write in this form first. This is what we call the standard form. Standard form for first order. And then what we do, we're going to calculate the integrating factor. So that's ix, which is the integral of px dx. We're going to calculate that, and then once you multiply by that, the whole equation automatically becomes, this side is y times the integrating factor, the product of that, and then the other side is simply ix qx. Now what we can do, we can integrate the two sides. Once you integrate the two sides, you're gonna get the integral of that, and you divide by ix. So we can write this one as ix, the integral of ix qx dx. What we normally do is we add the c there. So that's the formula you're gonna get for integrating factors. So you can try these problems. So this is exercise number 3. We can do A. You can do y prime plus 3y equal x e to the negative 2x, and B, you can try x y prime plus 2y equal sine x over x. Can do that. Number 4. So in number 4, what we're trying to do, so what we do is what we call the basic, the substitution methods. Substitution methods. So there are 3 methods. The first one is the what we call the basic substitution. Basic substitution. And the second one is what we call the homogeneous equation. And then the third one is the Bernoulli's equation. So let's talk about them one by one. So first one is the basic substitution method. So like I'm called type 1. So it's a type 1, the basic substitution. Basic substitution. So in this situation, what will happen, you get y prime is a function of some expression. So so this expression can be a expression of x and or y. So expression so you can see expression of x and y is most of the time the both variables. So in this case, what we're gonna do, if that's the case, we're gonna pick we're gonna make a substitution. We're gonna pick u equal that expression, whatever the expression, we're gonna pick that there. So that's the technique, and then after that we can take the derivatives and finish it. So let's look at it like a simple case here. So I'm going to give an example here because this is slightly different. So for example, y prime plus 1 equal y plus x minus 3 to the square, a situation like that. So in this case, you can see it's very clearly that is the function you're going to pick as u. So we're going to say u equal y plus x minus 3, take the derivative. So then it's y prime plus 1, and then you can see what we normally do is we're going to solve for y prime, which is u prime minus 1, and then you're going to substitute. So once you substitute that here, this side simply becomes u prime equal u squared, and then what we do, solve for u, and then after you solve for u, then we can use the relation here to solve for y. So that's what happened. So let's look at a different case also, like what if like you have something like this. So for example, 4y prime equal y squared plus 6x, something like that. And then you can see that the special format of this problem, you have y squared on the right side, on the left side you're going to see y prime. So that suggests something. So what we're gonna do, we're gonna substitute u equal y squared, because once you do that, you can see u prime by the chain rule 2y prime. So that means you can simply substitute that here. So if you substitute that, you can see this simply become 2u prime, and this is u plus 6x, and this is just a first order linear. So integrating factors, so that means use integrating factors, solve for u, and then after you do that, and then solve for y. So as exercise problems, you can try these. So this is exercise 4a. So 4a is 3ey y prime equal e to y plus 1. And if you think a bit, you can see that u equal ey works for this problem. Good, that's a type 1. So let's talk about type 2. So what is type 2? The homogeneous equation. Type 2, the homogeneous differential equation. Homogeneous differential equation. So homogeneous differential equation has two meaning. This is one meaning that we use in differential equation. We can talk about another meaning in a future video. So in type 2, what will happen, you can write the equation as a function of y over x. So if you can write the fxy function as a function of y over x, you call it is a homogeneous equation. That's a homogeneous equation. So if you can write like that, we call it is a homogeneous equation. Homogeneous equation. So if it's like that, then what we can do, we can make a special substitution. We can substitute v equal y over x. That's the substitution we use. And then this says that y equal vx. It's always the same substitution. And then what we do, we differentiate with this one. Once you differentiate, you're going to see that y prime equal v plus v prime x, and then we can substitute that to the equation and simplify. So after we do that, the goal is to solve for v and then solve for y. Good. So you can try this equation. So this is the exercise for that. Exercise for b. It is x y dy over dx equal x squared plus y squared. So let's talk about type 3 now. So what's a type 3? In type 3, we're going to talk about the Bernoulli equation. The Bernoulli equation. Bernoulli equation. So if you can write a differential equation in this form, we call this a Bernoulli equation. So we can write equation as y prime plus pxy equal qx and then y to the n. So if you can write a function, a differential equation like that, we call it is a Bernoulli equation. But there are two special cases that you need to consider, because those you don't need this technique. So for example, you can see that if n equals 0, this simply becomes the first order, this is just a first order differential equation. If n equals 0, just a first order, that means you can use integrating factors, so it simply becomes the first order linear. If it is first order linear, we know that we normally use the integrating factors. And then if n equal 1, if you n equal 1, you can see that so this is going to be a separable, or first order linear or separable. So it's going to be both. So you can use one of them. Either it is first order linear or it is the separable technique. So you can use one of the technique to do it in these two cases. And if n equals 0, first order linear. If n equal 1, it is first order linear or separable. So now the situation is, what if n not equal to any of them? So let's talk about that. So if n not equal to any of them, so if n not equal to 0 or 1, what will happen? You can divide the two sides by yn. So once you divide the two sides by yn, you can write this equation of y to the minus n y prime plus px y to the 1 minus n equal qx. You can write it like that. Now what we can do, we're going to make a nice substitution. We're going to substitute for this term. So whatever the term appear here, we're going to substitute for that. So so we're going to substitute v equal y to the 1 minus n, and then take the derivative. Once you take the derivative by the chain rule, this is y prime equal 1 minus n times y, you subtract 1, that means y to the minus n, and y prime by the chain rule. So this says that y minus n y prime equal 1 over 1 minus n v prime. So that's always the case. So there are two things here. So once you substitute this, you always get that. And it's very clear that n not t equal to 1 in this case, because otherwise you are dividing by 0. And then after we get that, we can substitute that into the equation. And once you do that, your equation becomes 1 over 1 minus n v prime plus px v equal qx. So you can see that this is a first order linear in v. Okay, so that means we can solve for v first using integrating factors. Integrating factors, and then after we do that, and then we can solve for y using v equal y1 minus n. Okay, so that's the technique. So those two are always the case, what is in the box. So you can try these problems as practice. So you can say for c x y prime plus 2y equal y cube sine x over we can say x, like that. Okay, so you can see the answers in the description. Good. So those are the substitution methods. So we talk about three substitution methods: the basic substitution, and the homogeneous equation, and the Bernoulli equation. And then let's talk about the last type, what we call the exact equations. So let's talk about that. So number 5. Exact equations. Exact differential equations. So in exact differential equations, what's going to happen? You have to write the differential equation in a special form. So we can write the differential equation in this form: mxy dx plus, it's very important, so plus sign, n x y dy, and then you set this equal to 0. So this is what we call the standard form. So you have to write it in this form first with the plus sign, and x comes first. Or you can write sometimes in some books you write this one as like this, still a plus sign, n x y y prime equals 0. So that's another way to write it. So but in both cases m comes first, so it's m and n. Now the first thing what we do is we check whether this is exact. So that's the first thing we do. So we can check whether da by m over da by y equal da by n over da by x. If they are equal, that means this is exact equation. So if it is exact equation, what we normally do is we know that if it is exact, so then there is a function of two variable function. So in this case, if this is exact, then there is a function fxy such that the x derivative equals to the m function, and then the y derivative equal to n function. So just pick one of them, and da by f over da by y equal to the n function. So that's what exact means. So there is a function like that. In this case, what we normally do is we can pick one of them, normally the easy one. So so we're gonna pick one of them. So let's say you start with the x function. So in the x function we're going to integrate with respect to x. So integrate with respect to x. So you're going to get the function xy, but remember this is a partial integration. So that means you're going to treat y as a constant. So you're going to see m xy dx, and then plus a. Since this is a partial integration, you're going to get a function of y. Now what we do after we do that, you need to find a relation between the m function and n function, because you have to find the goal is to find this. So we need to find what is this. Okay, so find this. To find that, what we normally do is we take the partial derivative and match with the other function. So so let's do that part. You take the partial derivative of this function. So it is a partial derivative of the function you just found, so which is the integral of m xy dx plus gy. But once you do that, what's going to happen, this gy simply becomes g prime, so we can take it out, and then you know that this this should be exactly equals to the n xy function. So we normally what we do is we set them equal, and then solve for g prime y. That's how we do. We solve for g prime y, and then after you do that, we're gonna take the integral. So we integrate, and then you're gonna get the gy. Once you get the gy, what you can do, you can go back and plug in. So you go back and plug in here, and then you get the function. So after we do that, then your solution becomes so the solution simply becomes fxy equal the function that you get m xy dx plus you found the g function, and you have to set this equal to 0, set this equal to constant. So that is the solution. So that means this part is going to give you the solution y as a implicit function. So this gives y as an implicit function, function. Okay, so that's the idea. And also you can use a shortcut method. So can use the shortcut method. So you can use a shortcut method that doesn't use the derivative step here. Okay, so as practice problems, you can try these. So you can try these problems as practice. So exercise 5. So you can say e to y minus 2xy dx plus 2x e to y minus x squared y plus 3 dy equals 0. So try this and you can see the solution in the description. Now the last type is what happened sometimes the differential equation, when you look at the differential equation, you can see that you do not get the exact equation. So you do not get to, so let's say so I'm gonna say almost exact equations. So solving almost exact. Solving almost exact equation. So so let's look at a problem like m xy dx plus n xy dy equals 0, and then we check the condition. So let's say what if dabba m over dabba y does not equals to dabba n over dabba. So there's a very good chance that this is the case. So that means it is not exact. So if it is not exact, in certain situations, not always, in certain situations we can solve this. So what we're gonna do, we can use integrating factor. So use an integrating factor. Use an integrating factor. Use an integrating factor I given by. So you can see that it is a little complicated, but I'm going to give you the expression for that. So so what happened? So we have to consider two cases. So what's the first case? If the my, the partial derivative of m with respect to y, minus nx, the partial derivative with respect to x of n, divided by n, if this is a function of x only, okay, it's a function of n only, then you can show that the integrating factor, which is a function of x only, is given by e to the same expression my minus nx over n dx. That's how you get the integrating factor. The other case, if nx, so you reverse the order, nx my over m is a function of y only. It's a function of y only, then it is integrating factor becomes a function of iy. It's a function of only y. It is e, the same thing. That expression goes here, nx minus my over m dy. So then you get the integrating factor. Now what do you know? That once you multiply by this integrating factor, your differential equation become exact. So then what happened? I times m dx plus I times n dy equals 0 is exact. Simply become a exact equation. Exact equation. So that means we can use the exact equation technique to solve the equation. Okay, so we solve it. So we can solve because it's an exact equation. Good. Those are the 6 major methods that we use to solve first order differential equation. And as practice, you can try these questions. So that's the practice. So this exercise number 6. This exercise number 6. So you can try the first one is 2y squared plus 3x dx plus 2xy dy equals 0, and b xy dx plus 2x squared plus 3y squared minus 20 dy equals 0. So you can try those and you can see the solution in the description. I would like to make a challenge. So see whether you can solve this problem at the end. So this is challenge. Challenge is solve xy dx plus x plus y plus 1 dy equals 0 using any of those methods that you know. Okay, see whether you can do this. Okay, this is a challenge. Can you solve this? Thank you.